the area of the gut-brain interface as it pertains to Alzheimer's really was something that we thought about 4 to 5 years ago. I built a collaboration with a gentleman named Gene Chang, who's head of medicine of GI here in the medicine section, University of Chicago, and he works on IBD and Crohn's disease, and he was somebody that I thought would help us in some way to figure out whether there is a gut-brain connection with Alzheimer's disease. And so he basically said, it's very simple. You treat animals with antibiotics and then see what happens. So, the paradigm is a little bit more complicated than that, but really not that much more complicated, to be honest. I had no preconceived notions of what would happen if you perturb the microbiome. Is the pathology going to get worse, going to get better? I'll take either one of those outcomes, and then we'll move on with that. And if nothing happens, well, we'll just leave it be. And, I wasn't looking for small 5 or 10% differences in pathology. I was looking for robust changes because, as a molecular biologist, it's, I'm very wary, especially with morphological approaches, but quantitative morphology, there are issues. But I also want to see a robust response. And so, we saw a robust response in terms of when you treat animals with antibiotics, you see you don't wipe out the bacterial communities, but what you do is you change the composition of bacteria. So those bacteria which are resistant to the drugs that we're using, they start to flourish, they take over, they colonize, and they become the preponderant strains that are present in the gut. And what we see in parallel and sort of correlative is that there's a significant reduction in amyloid burden, but it only happens in male animals. So nothing happens in female animals. We've done this in 2 different mouse. So we've done all these experiments in 2 independent transgenic mouse lines with different transgenes, with different insertion sites. It's get the same result, that it's a male-specific effect that of the reduction of amyloid burden at the time of sacrifice. Trying to look mechanistically what's going on, we clearly see that there are changes in plasma cytokines and chemokines in male animals, and they're in female animals as well, but they don't completely overlap. Is that meaningful? I don't know. It's just, there's a bunch of correlations, right, to the pathology and changing the microbiome. But the thing that we're most interested in is the biology of microglia, right? So we know now that the vast majority of genes involved in late onset disease, risk factors, ApoE, TREM2, CD33, et cetera, they're all expressed in myeloid cells, and they're expressed in cells of the innate immune system, and in microglia, being the innate cells in the brain, they express these at fairly robust levels. We looked at microglia, and we looked at transcriptome of microglia in this paradigm, and what we find is if you look at microglial transcriptomes in male animals treated with antibiotics, you see significant changes. A lot of genes are upregulated, several are downregulated, as you expect. But in female animals, nothing moves. There's really no change in the transcriptome following antibiotic. And so we think that that's underlies all these phenotypes, that the microglia, for whatever reason, are not getting activated to go after this debris for whatever reason. We don't know the reason. One thing I can tell you is that when we take male animals that have been antibiotics, where you expect that the amyloid load to be really significantly reduced, take another cohort of these animals and then introduce by oral gavage fecal matter from a transgenic animal or a non-transgenic animal, it doesn't matter, but like an animal that's co-housed. You now completely restore the pathology and you completely restore the transcriptome. And it happens in male animals. It's basically saying that something in the fecal matter, whether it's the bacteria or the metabolites, are positive. And so we're trying to figure out what's going on. Right? What is really underlies this? What are the molecules? What are the bacterial strains that may be involved in this? And then use those in sort of transplant experiments, as we've done in the past. But now we've generated germ-free mice for at least one of these strains. And in the germ-free animals, there's an reduction in amyloid deposition independent of sex. Why is that different from the antibiotic-treated animals? Who knows? I mean, it's just, it's biology. But it is true that germ-free animals also have a very, very immature immune system. That might complicate things down the line. We're ready for it. It's just the way goes. You know, we don't have many other choices. And so at least we'll have the germ-free animals, which we know when we introduce fecal matter into those animals, we can destroy pathology. So that's a good one. So I think that we should be able to do these sort of transplant type experiments with specific metabolites or specific bacterial strains to see which ones are important and which are driving it. Again, mechanistically, we don't completely understand, but we think it has something to do with the biology of microglia. So that's sort of our focus for the future.